So to graphically solve them, let's introduce some, parameters, because we have A, M, V naught, H bar cluttering our our problem. So let's introduce two parameters, gamma. Gamma is 2m v0 a squared divided by h bar. So in some sense, it's telling you how deep your square well is, as well as how wide it is, right? It's and the other one is alpha, and alpha is telling you how your energy is related to your potential energy. Okay. So just let me check something quickly. I'll be back. Right. So sorry about that. So alpha is defined to be square root of 1 plus E over V naught. Okay. So, remember that VE, the total energy, is less than V naught, right? And it's actually a negative number, but its modulus is, the modulus of this number is less than V naught, right? So this is a negative number which, whose modulus is less than 1, between 0 and 1. So this thing is positive as long as the modulus of E is less than V naught. Okay, so alpha is a constant which is measuring the energy of the particle in the box compared to the depth of the potential well. Okay. So now it's an exercise that you can show that, the condition that we wrote above, this condition, you can solve this, and the solution takes much nicer form. You get gamma times A. So it's a linear dependence on gamma, or sorry, on gamma. And this is equal to n minus 1 pi plus 2 cosine inverse of alpha, okay, where n is 1, 2, 3, dot, 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 okay? So the reason why these things come is because, you basically have to take some inverse of sine and cosine here. And because of the fact that you've got trigonometric functions, you get, different branches, okay? You get different branches. Okay, I want you to try this. And so let's look at this graphically to get some idea. So let's remind us what, what gamma measured. So gamma measured, roughly speaking, the product of the, it measures essentially the depth of the potential well, right? So if I hold, say, A constant, the width of the potential well constant, then gamma is going to give me the depth of the potential well. So what we see here is that if I, along the, x-axis, I have, I plot alpha, and if I look at the right-hand side, I'm going to get several branches of this, and let's, okay, let me just, yeah, so let's draw this. Use a different, so on the right-hand side, so these are the different branches. Also, let me make some room so I have more. I can go up in the Y direction more. Okay, good. So these are the we are going to be like drawing multiple things on the same graph. So first, for n equals to 1, we are so our right-hand side is going to be something like this. Okay. So here, alpha goes to 1. Of course, alpha cannot be greater than 1. And then for and here we have the first branch. And then the second branch is going to be just shifted by a constant amount. Sorry. So if I look at this equation, it is, every branch, this is essentially what is changing. So it's pretty easy. Once you've plotted one, you can plot all the others. So this is, but I should be, yeah, they should all go to the same. Okay. Okay. So this is the right-hand side of the equation. And the left-hand side of the equation, it's just, this is just this guy. And we are plotting, so this is not, this should be alpha. And if I take the different values of gamma, which means I am changing the I'm changing the depth of the potential well, then I will get lines of different slope. So for gamma 1, you find a straight line. This is gamma 1. For gamma 2, it'll increase. And at some point for gamma 4, you will find that it goes something like this. Okay, so this is gamma 4. And then this rapidly increases. For gamma 12, goes something like this. And for gamma infinity, what it'll do is that it'll just go in that direction. Okay. So in gamma so what are the solutions? The energy eigenvalues are going to be given by these intersections. Okay. This is the I did something slightly wrong here. No, it's actually fine. Yeah. So so these are going to be the energy eigenvalues. Okay. Any questions? So for a very shallow potential well, we are going to have the shallowest potential well that we can have. We are going to have a. This is going to be the potential energy, but in contradiction to what I said before, we see that if I decrease the the depth of the potential well, what happens is that this gamma, the slope of this line decreases more and more. But how it doesn't matter how shallow the potential well is, it's always going to intersect with this first curve, right? Do you agree? So that means that there's always going to be one solution. Okay. So this is in contradiction to what I said. Okay, so but as you increase the depth of the potential well, you're going to have more and more. So for example, when gamma is 4, you're going to have 2 solutions. When gamma is 12, you're going to have 1, 2, 3, 4. Okay.
So what does the solutions represent, like the intersections?
Oh, you're just, I mean, these solutions, so basically these are just, yeah, exactly. You're solving this equation. Let me just, copy that equation. You're solving a transcendental equation, right? You're solving a transcendental equation. Transcendental equations are kind of hard to solve. So the idea is that you don't have a closed form solution for your energy eigenvalues. The solution to those, the energy eigenvalue is given by, so all you've managed to do is to find a constraint on the energy eigenvalues. And this is that constraint, this transcendental equation. So in physics classes, we are told that when you cannot solve a transcendental equation, what do? You try to solve it graphically. So what I've done here is that we have, we have basically plotted the left-hand side and the right-hand side. The right-hand side is given in green for different values of n, and the left-hand side is given in terms of red. And what we are doing here is that we are changing the depth of the potential well, and the depth of the potential well is given by gamma, and alpha is telling you essentially the energy. It's giving you the energy in some units. And alpha, this equation makes sense up to the value of alpha equals to 1, because you know that the argument of cos inverse cannot be greater than 1, right? So that's what we're doing here. And so what I'll do is that in the next class, we'll do an analysis of this, of these solutions, and then what we'll do is that we will come up with a way to try to understand more general solutions, right? So we have, kind of ran out of time. In the next class, I will discuss the, what are the forms of the wave function, and and stuff like that. Okay.